So there are factors that affect equilibrium, and a reaction at equilibrium can be knocked out of equilibrium by one of these factors we're about to discuss. There's this principle called LeChatlier's principle. It's a French thing. Pronounce that however you wish. That's how I'm going to say it. LeChatlier's principle says if an external stress is applied to a system at equilibrium, the system adjusts in such a way that the stress is partially offset as the system reaches a new equilibrium position. So a system sitting at equilibrium, you whack it out of equilibrium, and it works to reestablish equilibrium. That's what that is. You stress a system, it will respond. How does it respond? Well, we got to talk about that. What are some of the stresses that you apply? Well, we got to talk about that. One of the stresses that you can apply is changing concentration. So in this given reaction, if I have the system sitting at equilibrium, that's going to mean there's some of each of the components present in my reaction flask, whatever that is. If it's sitting at equilibrium, there's a steady state concentration of every component present. It's not that they're all equal concentrations, but it's a steady state concentration. So if I knock the system out of equilibrium by adding some extra product, the equilibrium will shift left to offset the stress that I applied. So I've added some NH3 that causes, taking it back to last week, your reaction quotient, your Q value, which is products over reactants, that causes your Q value to get too big, so you shift left to create more reactants to make your Q value smaller again to reestablish Q equal to K. How does this look graphically? Well, it looks like this. So if I had a system sitting at equilibrium, I had this much H2, this much NH2, this much N2, I stress the system by all of a sudden, instantaneously, that's my snap fingers, instantaneously I add some NH3 and I reestablish equilibrium by declining the NH3 concentration, increasing the reactant concentrations. Your starting equilibrium and final equilibrium concentration values of H2 and NH3 and N2 are not the same. So your concentration values in the beginning and in the end change, but your K value stays the same as long as you're at the same temperature. So let's see what that means for other reactions. If you have a simple, standard, generic reaction, anytime you add products, the reaction will respond by trying to consume the extra products you added, which means creating more reactants. It will always shift left toward reactants, okay? If I stress equilibrium by removing some of my products, that means there's not as much product as there should be to make Q, the reaction quotient, the size that it should be, so the system responds by shifting right to create more products. You take away products, you got to replace what you just created. Nope, that's you take away products, you got to create more of what you just removed. You can also add reactants. Anytime you add in reactants, the system responds by creating more products. Trying to consume the extra reactants you just added, it shifts right. And our final option is if we remove some reactant, the system will respond by trying to replace the reactant that you just removed, so you will shift left toward reactants. So, yeah, that's changes in concentration. Concentration is one of the stresses that we can apply to a system at equilibrium and see how it responds. Changes in pressure is another thing that we can do, another stress that we can apply to a system and see how it responds. So this system is all gases. So we've got a chamber full of stuff. It's got some products, some reactants. See, there's a little NH3 and a bunch of N2s and a bunch of H2s. Yeah, it's at equilibrium. Q equals K at equilibrium. If I push that piston down, what I'm doing is the pressure inside the system gets greater because I shrunk my volume. You may remember that pressure and volume are inversely related. So I decrease my volume, which increases the internal pressure of the system. Q is no longer equal to K. So Q needs to change to reestablish Q equal to K. That's what happened over here. So if we look at our little picture, I have 1, 2, 3, 4 N2 molecules in my Q not equal to K picture. And then over here, I have 2 N2 molecules. So that actually tells me that this reaction shifted to the right to create more NH3 molecules. How does that work? Why does it work that way? Well, I'm going to click through a couple of things and I'll give you the take-home message. But we can calculate Kp for our initial reaction if we just pull some values out, just make up some values. If the pressure of NH3 is 2, because we've got 2 of those molecules, that's why I chose that. And 4 for N2 and 8 for H2, that gives me a K value of 0.002. Well, in my new system, I have doubled the pressure because I've halved the volume, double the pressure, so I can calculate my Q value as 2 times the values that it was before. I know that it does not look like I have not increased the number of particles. No. I have just halved the volume, which increases the pressure automatically. There's my Q value. Q is smaller than K, so Q needs to grow, which means I need to increase the concentration of products. So that's how I shift the direction that I do. Q's less than K, so I shift to make more products. How does this work for gases? In general, when the pressure is increased, the internal system pressure is increased, the reaction moves toward the side, the reaction shifts toward the side of the reaction with the fewest moles of gases because the reaction is trying to reduce pressure. So in this increased pressure system, the reaction shifts, not always left or right, it shifts toward fewer moles of gas. So on the right-hand side of this equation, I've got 1, 2, 3, 4 moles of gas. You get that? 1 plus 3, 4 moles of gas. On the product side, I've got 2 moles of gas. So you shift toward fewer moles of gas. If the pressure is decreased, as in let's increase the volume, which means decrease the pressure, you're going to shift towards more moles of gas. It's just an equal and opposite kind of reaction. So let's go through a couple of things with this example down here. If I decrease the pressure, that means increase the volume, decrease the pressure, you'll shift toward more moles of gas. And in this given equation, that means shift toward reactants. If you increase the pressure in this bottom reaction, that will mean you shift toward products because there's only 1 mole of gas over there. So concentration stuff, you always shift one direction or the other based on whether you're adding or removing products or reactants. But in pressure and volume changes, it's always dependent on the reaction equation, and you shift toward greater or fewer moles of gas. Okay, concentration is one thing, pressure is another thing, temperature is another thing, another stress that we can apply to a system to knock it out of equilibrium. So, given this reaction and this enthalpy value, do you remember enthalpies? Negative enthalpy value means exothermic. So I always think of exothermic as heat is thought of as a product in this reaction. So if I rewrite that exact same reaction but add heat as a product because it's an exothermic reaction, to me that makes this concept of temperature and equilibrium much easier to understand because I feel like it's intuitive the way that concentrations are sort of intuitive. So if I increase the temperature, it increases the thermal energy reaction, that means I'm adding more heat to the reaction. Just like adding a product, it's like adding more heat to the reaction. This reaction responds, all reactions respond, by trying to reduce the heat output. Because this one is exothermic, if I increase the temperature here, equilibrium shifts to the left toward products to try to decrease the extra heat that I've added. In this reaction, if I decrease the heat, decrease the temperature, That means the system will respond by shifting right, trying to generate more heat. So exothermic reactions, think of heat as a product. Endothermic, think of heat as a reactant, and then it shifts the same way that concentration would. Let's give a summary. In general, if I increase the temperature of an exothermic reaction, K decreases. Wait a minute. Concentration and pressure do not change the value of K, do not change the value of the equilibrium constant. But temperature changes the value of the equilibrium constant. So it's not just that you're shifting to make more or less of this. You do that, but your K value changes in response to your changing temperature as well. So when you increase temperature, K will decrease for an exothermic reaction. That's because your reaction is shifting to make more reactant, which means making your denominator bigger. That's why K gets smaller. Really, truly, guys, I do not memorize this junk. I talk it through all the time. For an endothermic, that means you're adding extra heat over here, which means it will shift to make more products, making your numerator bigger. K increases. Conversely, when you decrease the temperature for exothermic, K gets bigger. For endothermic, K gets smaller. I talk myself through why that happens the way it does without memorizing this, but you're welcome to memorize it if you would like. Okay, what's next? Something else that could be considered a stress to a system that could be considered something to knock it out of equilibrium, adding catalyst. It does not change your K value. In fact, it does not shift the position of equilibrium whatsoever. So when you add a catalyst, it doesn't mean you're going to create more products. It doesn't mean you're going to create more reactants. It just means the reaction happens faster. You reach equilibrium faster. So two reaction coordinate diagrams for your viewing pleasure. A typical reaction coordinate can look like this. There's a big hump in the middle. We'll talk quite extensively about that big hump in Chapter 13, but that big hump is called the activation energy. If you put a catalyst in the reaction, the activation energy barrier is smaller. The catalyst lowers the activation energy for the forward and the reverse reaction, meaning A becoming AB, climbing up that hill to become CD, or CD climbing up that hill to become AB. It's smaller activation energy forward and reverse than it was without a catalyst. So this is with a catalyst, this is without a catalyst. The catalyst does not change equilibrium. It does not shift equilibrium to create more products, more reactants, all that stuff. So in summary, there are several factors that affect the position of equilibrium. We've talked about concentrations. Do they shift equilibrium? Absolutely. Do they change your K value? Absolutely not. Pressure can shift equilibrium. For sure. Does it change your equilibrium constant? Absolutely not. We're going to talk about that little thing in a second. Absolutely not. Volume is another one. Does it shift equilibrium? Yes, because pressure and volume are related. Does not change your equilibrium constant. Temperature does shift your equilibrium to create more products, more reactants, etc. It also changes your equilibrium constant. It's the only one that does. Catalyst does not shift equilibrium, still does not change your equilibrium constant either, for sure. So for concentration and temperature, well, let me just say, for concentration, we can say if you add more products, it's always going to shift left. If you add more reactants, it's always going to shift right. For pressure, you cannot say if you increase the pressure, it always shifts left or it always shifts right, because it depends on the reaction and how many moles of gas you have. That's what that little asterisk is saying. You can't always say it shifts left or right. It depends on the reaction you're given. Temperature, for the same thing, it depends on whether it's endothermic or exothermic as to which direction it shifts. Okay. A couple of examples we'll walk through quickly. Consider the following equilibrium process between dinitrogen tetrafluoride and nitrogen difluoride. Predict the changes in equilibrium if the reaction mixture is heated, the reacting mixture is heated at constant volume. Okay. I'm told this is delta H, meaning the reaction is endothermic, so I add heat as a reactant to an endothermic reaction, and heating a reaction means increase this little heat value, so it shifts away from the increased heat, meaning the reaction shifts right toward products. The reaction responds to the increase in heat by creating more product. We'll use those kinds of sentences. Okay, B. Some N2F4 gas is removed from the reaction mixture at constant temperature and volume. Okay, so if I remove a product, the system will respond by trying to replace the product that you removed, so it will shift left toward reactants. Okay. The pressure on the reacting mixture is decreased at constant temperature. Okay. Pressure. Well, I've got 1 mole of gas creating 2 moles of gas. So if my pressure is decreased, that means the system will respond by trying to increase the pressure. So the reaction will shift right toward products because there are 2 moles of gas present in products. When the external pressure decreases, the reaction responds by trying to increase internal pressure, meaning it creates more moles of gas. A catalyst is added to the system. It don't do nothing. Equilibrium doesn't shift. That one's real easy. A couple more examples and then we'll be done with this. If I have this reaction and increase the pressure, so I'm increasing pressure, the system responds by trying to decrease that extra pressure I've added. Trying to decrease pressure will mean creating fewer moles of gas, and in this reaction that means shifting to the right 2 moles of gas versus 3 moles of gas, shifting right. Removing O2, so that means removing a reactant, you got to replace that, shift left. Okay. Decrease pressure. The system responds by trying to increase the pressure, and increasing the pressure will mean favoring more moles of gas. More moles of gas means favoring the reactants side, shift left. Increase volume. Increase volume means decrease pressure. Decrease pressure means the system will respond by trying to increase the extra pressure you have removed. Increasing the pressure means making more moles of gas, shift left. Decrease pressure, because the pressure is one of the hardest ones. Decrease the pressure means the system will respond by trying to increase the pressure. Increasing the pressure means favoring more moles of gas. There's 1 mole of gas on each side. So because there's equal number of moles of gas, Q doesn't change. The reaction doesn't shift. Oh, this is a long one, but we're wrapping it up. At this temperature, the equilibrium constant Kc is this value. In a certain experiment, the equilibrium concentrations are these things. Suppose some NH3 is added so that its concentration is increased to that much. A. Use LeChatlier's principle to predict the shift in direction of the net reaction to reach a new equilibrium. Confirm your reaction by calculating Q. Okie dokie. NH3 was the concentration when it was at equilibrium, but we have increased the concentration of NH3. So A, the reaction will shift left to right, left to right, left to consume to consume products, to consume the extra NH3. Okay, confirm your prediction by calculating Q. Q equals 365 squared. I should have written out the expression, but the video is long enough already. Times the other concentrations did not change at the instant. I always snap my fingers for that. At the instant that you added the new stuff, the concentration of other things did not change. They will change in response as the system begins to respond, but they don't change at the instant that you added new stuff. So I've already got this math worked out on a sheet of paper. Hold please. 0.0286 if I did my math correctly. So 0.00237, I believe, if I did that one right. So Q versus K. K is smaller than Q. And because K is smaller than Q, the Q will need to decrease, which means the product concentrations need to decrease, the reactant concentrations need to increase, so they will do that. That is true. When we said when Q is greater than K, it will always create more reactants. All right, I'm done with this one. Whew, that was long.